An aircraft that pitches up when climbing or maintains steady level flight while cruising in a changing atmosphere or pitches when landing all require special adjustment of elevator control surfaces, which the pilot directs with the push and pull of the cockpit control column. Now, the pilot will get a well-behaved response, but enabling this behind the scenes is an automatic fly-by-wire flight control system. In this lesson, we examine such a control system, specifically a pitch rate tracking controller. It allows well-behaved pitch orientation response to the push and pull of the control column. Our primary learning objectives are to understand the architecture, how to tune it, and its effect on the airframe. When the pilot pushes and pulls on the control column, a transducer turns the mechanical motion into an electrical signal commanding aircraft pitch. More generally, the pilot manipulates the cockpit controls, which sends electrical signals to the flight controller to command a change in the aircraft state. The flight controller sends an electrical signal to the control actuation system, such as a hydraulically driven elevator. This in turn changes the aircraft state, and the translational and rotational response is fed back not only to the flight control system, but also the pilot, who perceives the handling qualities of the aircraft and decides what further control adjustments may be needed. This feedback loop represents a process to rapidly and efficiently drive the aircraft to a desired state. It can be represented as a single process with command input and achieved state output. In this case, we're talking specifically about a pitch rate tracking control system, where pulling the column back creates smooth and responsive pitch up motion, and pushing the column forward creates smooth and responsive pitch down motion. To proceed, let's define a few variables. We're going to work with the longitudinal dynamics of a transport aircraft model. It has a body fixed axis out the nose. Pitch is the angle between that body axis and the horizon. The elevator angle is from the body axis and negative down. And the angle of attack is from the body axis and the velocity vector. Finally, we're going to develop and analyze the pitch rate controller from a steady and wings level trimmed state, pitched up 9.7 degrees and flying at 250 feet per second forward. Now, what's the architecture of the controller? We start with the pitch rate command. This is compared to the achieved pitch rate from the aircraft to produce an air signal that is amplified by a gain and integrated. The pitch rate is also multiplied by a constant gain, and these two signals are added to produce the elevator command, which goes into the control actuation system, which produces an achieved elevator response that affects the aircraft dynamics. And this process continues so that the achieved pitch rate converges to the commanded pitch rate. This is a proportional integral control architecture, algebraically expressed in the frequency domain, also in the time domain. And finally, we note that the pitch rate Q is the time rate of change of the pitch angle theta dot when confined to the longitudinal plane. So going forward, we'll use pitch rate Q in our formulation. Now there's two loops in the feedback control system. A proportional control loop that tends to drive the pitch rate to zero. That is, as KQ increases in magnitude, it tends to dampen oscillation in the pitch rate response. There's also an outer loop for tracking pitch rate commands. As the integral air gain increases, pitch rate will tend to track the command faster, but this could introduce oscillation, which KQ would have to be adjusted for in response. Now, overall, this single integrator indicates a type 1 control system That's going to provide asymptotic tracking of constant pitch rate command inputs. To proceed with analysis and tuning of this controller, we're going to work with both frequency and time domain models, and being able to fluently work in both domains is a very powerful skill set. We're going to implement the pitch rate tracker with a nonlinear aircraft simulation. So the controller represented in the time domain is going to be very convenient. As a linear model, we can write the controller in a linear time invariant form. Here, the subscript C is for controller. Y is the plant output, in this case Q, the pitch rate, and R is the commanded pitch rate, or the command input. We need to write the integrator as a dynamic system. So first, we define the tracking error as Q minus Q command. And the integral error of Q. Now, take the derivative of the integral error to get the error, and in doing so, we create a dynamic system where the matrices can be immediately identified. The dynamic controller produces the elevator deflection command, which is input to the control actuation system, which is an input to the longitudinal flight dynamics. Here, another LTI system about the trim condition presented earlier, which produces the pitch rate response that's fed back into the controller. The flight dynamics capture small deviations in state and control inputs about the trim condition. The four states here capture the phugoid and short period mode, which are controlled through elevator and thrust input. The control actuation system is a simple first-order ODE, a low-pass filter. We set the eigenvalue to -1, which is on the order of 0.1 Hertz, and would be considered very slow in terms of actuation. This time domain feedback control loop is equivalent to the frequency domain loop shown earlier for the special case of LTI flight dynamics. We now have a closed loop system defined with two parameters, the gains, that dictate how well the tracking is achieved. Without going through a massive trial and error exercise in the nonlinear simulation, we ask how we can efficiently understand the choice of the gains on the closed loop system response. We start with a case of low control effort or low gain, where blue circles denote the open loop eigenvalues and white dots are the closed loop. We identify the process to which each eigenvalue corresponds: the actuator, the short period mode, the phugoid, and the integrator. We vary the integral error gain for increased tracking performance with a small proportional gain for damping. This root locus shows us a tough trade-off. As the integral error gain magnitude increases, so does the rate of tracking, but the short period approaches the right half plane, becoming increasingly underdamped. Simultaneously, the phugoid damping increases as it approaches the real axis. At some point, the phugoid dominant pole moves rightward on the real axis, slowing down the phugoid mode as control effort increases. We attempt to artificially dampen the system further, now setting KQ from -5 to -20. This shifts the short period, but does not affect the damping. Increasing artificial damping further is ineffective in this example. Further, the phugoid appears unaffected by the change in KQ. Given the poor trade-offs between gains, The strategy is to select a lower value of integral air gain to maintain as much short period damping as possible while obtaining sufficiently fast tracking. As we'll see later, the culprit in all of this is the low speed of the actuator, which cannot respond fast enough to compensate for the rate of change in the short period. But for now, we'll assume that we're stuck with the present control actuation system. To assess robustness, we use classical stability margins. Toward this, we're going to generate a series of Nyquist diagrams. Now, for an open-loop stable system, the Nyquist stability criterion says that the closed-loop system T is stable if the loop gain Lu, evaluated along the Nyquist contour, which encloses the right half plane, if that loop gain encircles the critical point -1 p times, where p is the number of right half plane open loop poles. In this example, our open loop system is stable, so we look for the loop gain to cross the critical point. That is, stable being to the right of the critical point, and unstable. For the stable system, the distance away from the critical point is a measure of robustness. The classical distances for robustness are gain margin and phase margin. Vector margin, a lesser known but also important metric, is the smallest distance to the critical point. It can capture sensitivity that the gain and phase margin miss. Now, to determine the loop gain transfer function for our example, we first determine the controller transfer function K and the plant transfer function. Note that the plant here is the actuator and rigid body dynamics connected in series. Now the loop gain, Lu, is simply their product, P times K. As the integral air gain becomes more negative, we can see how the loop gain approaches the critical point. The margins simultaneously decrease. Here, robustness is in the sense of a scale factor or phase lag at the plant input. So as the integral air gain becomes more negative, greater control effort is being applied, consistent with greater control performance. But this is occurring while the robustness consistently decreases. This performance-robustness trade-off is most apparent when looking at the step response side by side with the Nyquist diagram. As tracking performance increases, the robustness decreases, but the transient response leaves much to be desired. In fact, this closed-loop step response looks absolutely terrible. But from the root locus, we know we don't have a lot of ability to dampen out the short period. And we could observe both modes in the step response. We have the short period oscillation and the longer period phugoid, which draws the steady state response away from the constant command input. You see, in this example, we're tuning a short period controller with a model that contains the coupled short period and phugoid 4-state linearized equations of motion. This makes our tuning job a little more difficult, but this coupling will exist in the actual aircraft dynamics, so we must learn to deal with it. Now looking back at the open loop dynamics, we can see that the elevator input directly excites the pitch rate, a state associated with the short period. The pitch rate also affects the angle of attack, the other state associated with the short period. So what we have highlighted is simply the short period dynamics, which could be extracted and independently analyzed. But keeping with this system, note that as the elevator changes the pitch rate, it also affects theta, the pitch angle, which is associated with the phugoid. And we can see that pitch angle changes airspeed, and changes in angle of attack also changes airspeed. So we conclude that the short period is excited through the elevator, and the phugoid is excited through the short period. That is, the short period is coupled to the phugoid mode in the A matrix. Let's decouple the modes and control the short period only. For this, we'll set the cross-coupling terms to 0. Now, the short period does not excite the phugoid mode and vice versa. In the decoupled system, we find a mean steady-state tracking of the pitch rate. And as a type 1 controller having a single integrator, it's consistent with our expectations. So this exercise shows us modal coupling. But in the end, we can't decouple the modes with this control architecture. But at least we understand the effects, so we're not left wondering when analyze the controller in a nonlinear simulation. Here we're going to track pitch rate commands about this trim condition. We use the stability axis longitudinal equations of motion. We won't go into their derivation or assumptions here, but the list of variables will be appended at the end of this video. Our tuned control system has an integral gain of -70 and a proportional gain of -20. Let's pause for a few moments and observe the results. Running the simulation and comparing the linear to the nonlinear equations of motion, first, we find excellent agreement between the two sims. And second, we see that the short period and phugoid in the pitch rate response as expected. The step pitch command would be like pulling back on the control column, which, as we can see, produces a reasonably well-behaved pitch angle response in the airframe. A doublet's now commanded, simulating a pull-push-release on the control column. We observe pitch up, then pitch down motion, peaking at roughly 10 degrees above the trimmed pitch angle. We can also see a gradual elevator response to the commanded pitch action. The symmetric push-pull of the doublet, while applying constant thrust, in the end leaves us slightly off the original trim condition. Animating the pitch rate doublet, notice the gradual change in elevator motion consistent with its eigenvalue of -1 or approximately 0.16 Hertz, an unrealistically slow actuation system. But many lessons to be learned in going through the exercise. Now, let's assess the controller for a more realistic, faster control actuation system. Here's our previous control system with the gains and actuation time constant highlighted. We now reduce the time constant by 2 orders of magnitude. In doing so, we need to retune the controller. We'll select new gains based on a quick root locus analysis. Setting the pitch damping gain to -500 provides a completely different pattern for the short period eigenvalues. The short period becomes critically damped, with eigenvalues on the real axis. As the integral air gain is scaled up, the short period eigenvalues approach each other and split along opposite trajectories at -761. The phugoid follows the same pattern as before. We select gains for the fastest short period response that's still critically damped. With the updated actuation and PI gains, we simulate the doublet command input response. As before, a 3 degree per second amplitude doublet was commanded, simulating a pull, push, return motion of the control column. We observe much faster pitch rate tracking that's critically damped. Pitch angle linearly increases to 20 degrees, then nearly returns to the trim condition without oscillation. The faster actuator enabled autopilot tuning for improved closed-loop performance, specifically rapid tracking that's appropriately damped, and by inspection, no phugoid coupling into the pitch rate and pitch angle response. Observe the difference between the slow and fast actuation scenarios. Note the rapid motion of the fast actuator on the right, that through the flight control system provides an overall improved pitch orientation response. Recall our learning objective was to understand the pitch rate tracking control architecture, its tuning, and its effects. Toward this, we introduced a PI pitch rate tracking controller, which only relied on pitch rate feedback. We explained the state space formulation of this controller for analysis and tuning in the time domain. We then tuned the controller with a root locus, Nyquist diagrams, and step response plots. And in doing so, we illustrated the effect of modal coupling on the closed-loop response. Moving on to the nonlinear simulation, we showed the effectiveness of the pitch rate tracking controller. We also compared our results to the linear simulation. And finally, we sought to improve controller performance with faster actuation and briefly re-examined the achievable performance. From this lesson, we've learned that the pitch rate tracking controller is effective for pitch orientation control in the sense of providing a responsive and well-behaved change in the pitch angle due to push and pull of the control column. In this, we saw how modal coupling can complicate tuning, and this led to the idea of starting simple with the essential dynamics to be controlled analyzed first, and this would help us isolate cause and effect. We also showed how actuation performance can be critical to achieving closed-loop airframe response, and that adequate pitch damping combined with faster actuation was key to providing an airframe fast and damped short period response through integral air gain tuning. A few other considerations to mention in the future. Towards readiness for actual implementation, we would need to tune controllers for an entire flight envelope versus the single point considered here. We'd also need to examine control effectiveness with coupled lateral dynamics in both linear and nonlinear simulation. And actuator rate and angle limits reduce gain and phase angle of the actuator response. Such limits would be imposed in a real system, and so they should be analyzed at this level of control tuning. This is Flight Control Fundamentals, Section 1.4. Access this lesson and more at learngnc.com.